Swayam Prabha. Digital India. Educated India.
Welcome back. Just our usual wheel summary, and let's do some synthesis. I mean, we've done a lot of reactions here, so let's do some synthesis as well, because that's pretty much the goal of most of these reactions, is to make something out of it, right? So let's look at, we didn't have too many reactions, so NBS and peroxide, chlorination, bromination, those are the main ones that we did. So NBS, the unique thing about it, it is allylic, and the unique thing about the peroxide HBr, it's anti-Markovnikov. And bromine and chlorine, the unique thing is the stability rating tertiary, much more than secondary, and so on. And here you get mixtures. So let's do all of this. And NBS and NCS are pretty much, you know, the close cousins. Is just chlorine instead of bromine here. So we have choices here. Allylic, I'm just going to put an A here, or here, or here. And these two are pretty much going to be the same. If I put it here, it can give you a tertiary radical here, your major product. So you can have major product being a tertiary. Let's do a radical here, and then put your bromine right there. So you do get bromination, and it's going to be here. Since that's a tertiary, you know, that might be a major product. You can also put it on the sides here, okay? But this is probably the least favorable because it's primary, and so you may not really want to go over there. You can put it over here, but that's still secondary and not tertiary. And so you can also do this for bromine. That's a secondary. And typically, tertiary is more than secondary. All right, and that is going to be another one right here with the radical here, and you also will put it over here or here. So all along this, you will be putting your bromine. Okay, I'm just going to draw a few. Same with NCS. This is probably going to be a lot more selective than chlorine, and since I'm just going to put major, I'm going to put the major product here, chlorine. Here you have peroxide, and as I said, with HBr, it's going to go anti-Markovnikov. So there's no cation, there's a radical, and radicals prefer to be tertiary, so your bromine is going to attack here and push this to a tertiary radical, which is then going to go in and react with your hydrogen, and that's why it's going to be anti-Markovnikov, because tertiary radical is the best, at least in this case, where you don't have a choice of going a benzylic or allylic. All right, so that's your major. Well, if you add bromine into this, you're going to get anti-bromination. So here, if you hydrogenate, let's say, if you add bromine, you have a tertiary hydrogen there, and that's where your bromine is going to target, tertiary, and it's a chain reaction. And this is going to be more than 98%, or let's say more than 95%. Whereas with chlorine, you're probably going to get a mixture, but still your tertiary is going to be more. This is going to be your major. But you would have your secondary minor as well. So you can have your chlorine here as well, and that will be your minor product, or here. And if you have, if you don't have an excess of starting material, you should have an excess of starting material here. Otherwise, you can get polychlorination. On the same molecule, you'd get chlorine in multiple positions. But if your chlorine is going to be a limiting reactant and it's going to go search around for one of these, then by the time it searches for that, then the others would have gotten the rest of your alkanes. So you only have a possibility of putting it on one carbon and not multiple. So basically, if you want to reduce mixtures, have an excess of this, of polychlorination, putting 2 or 3 chlorines on the same molecule. For bromination, as we talked with those graphs before, it's much more selective, much less reactive. So this is going to be your choice for halogenation, and not really this, because of the mixtures, right? You don't want to spend half your life sitting in the lab trying to get those separated. All right, let's look at some synthesis. So here is an alkane that became an epoxide. All right, let's try to see how that happens. So again, we talked about synthesis, and we said first try to find your starting material in your product. 2, find the functional group chain changes if there are any alkyl changes. In this case, the functional group change is putting this epoxide, this oxygen getting on here. That's the only thing that really changed. Everything else is the same. There's no change in the R groups. They are the same. So we didn't have like a major ozonolysis or some oxidation which kind of blew off a carbon. We just, having the same number of carbons. So, well, then the next thing we do is try to work backwards to see how these functional group changes happened. All right. So let's start with the product and then try to work towards the starting material. All right. How do you make an epoxide? So you go back, look at all your reactions, and you will see to make an epoxide, you absolutely need to have a double bond, and then you put some peroxide on it. So your starting material to make an epoxide is to start with an alkene. So there's your alkene. So then our next goal is to try to make an alkene from an alkane. Well, alkanes, they're not reactive, they're just gasoline which you burn, combustion. Anything else happening on alkanes out there? Yes, this reaction. So that's the alkane, that's pretty much the only other alkane reaction that you really know of other than combustion. So if you have a synthesis, and you have an alkane starting material, the first step has to be functionalizing that alkane with bromination. Alkene, so you're working backwards to make an alkene. Think. You got to have an E2. To have an E2, you have to have a good leaving group, either an OTS or a bromine or a chlorine or an iodide. So, well, we already said bromines are also easy to put on. So we're going to go with a bromine here because it's the easiest one to put on with bromination. All right, so here's an E2, and then here's a peroxide. So you can use MCPBA, and that comes with the solvent dichloromethane. Here's an E2, and this E2 we're doing the most substituted sites of E2. So we know we don't need a big base for that because that's going to put the alkene here. We don't want that because the epoxide is not hanging out here, it's hanging out here. So therefore, we want to put a small base like sodium methoxide, and this is tertiary, so there's no SN2. So it's all going to be E2. Okay, it could be methanol or DMF or some aprotic or protic solvent here. All right, and then this is where our guy comes in, bromine, and we want to put the bromine with HNu. There you go. So we did it. So we put a bromine, did an E2, and did an epoxide. All right. That's kind of, well, looks, in hindsight, it looks kind of easy compared to this guy. Why is he hanging off the wrong place? Oh, well, let's do the same thing. Let's work backwards. So here, you want to put the epoxide where an alkene was, probably here. And so we put MCPBA, and we can do the same thing. All right. Which means you got to have an E2 happening. All right, and you want to have an E2 happening here. How is that going to happen now? To do an E2 over there, that's going to be a lot harder, you would think, because that's like the preferred place for an E2 is the most substituted. So probably you had a bromine here that made an alkene here with potassium T-butoxide. That's a possibility, right? Because this is the less substituted. So therefore, to get the less substituted alkene, you got to have the bromine here. All right, so how on earth are you going to take this and put a bromine at the less substituted position? To put a bromine here, if you look at it, you can see there is kind of a similarity. Here is your tertiary and next to that is your bromine. So this is anti-Markovnikov, which means you have to have an alkene here and you can put the bromine here. So you have a double bond here, which you did an anti-Markovnikov addition. So HBr with peroxide. All right, which means how do you then put an alkene over there? Well, you have to start with your alkane to alkene. We already did the same thing. We put a bromine and did an elimination. So this step is pretty much going to be the same. Bromine and an E2. Okay, so this is the same as this. So we can do the same thing over here. You put a bromine, Br2 with an H nu, and then we take it off with, you don't want Kotbu because Kotbu is going to give you a less substituted alkene. You want a small base, and sodium methoxide will do the job, mainly because there's no SN2 and there's only E2. There you go. So any epoxide that you see, you can make from an alkane by going through an alkene. All right, and to do an alkene, you got to brominate and do an elimination. Then you can do other reactions. So all the reactions on alkenes, let's say they put a diol, then you choose a osmium tetroxide. Let's say they put a chlorine here, then you just choose HCl. They put an OH here, that's a sulfuric acid dilutive. You know, so you have so many options once you come to alkene. And same if you have epoxide and then they give you something else with something added here, then you know it's just an SN2 after this, right? So that's pretty much how you have to like expand your thinking, okay? Go from functional group to functional group and you bring in the reagents. All right, so here's a guy and you got two double bonds here. Well, I know we know how to make one double bond, but how do you make another one? Well, let's first make that one double bond first. Well, which one do you think you're going to make first, this one or this one? Well, you know the bromine can only go on the most substituted, so you can make this one first. All right. So then after that, how will you make this double bond? Well, you got to have one elimination and a second elimination. So in order to have a second elimination, you got to have a good leaving group. And so if you want to put a leaving group here next to a double bond, I hope a light bulb's going off in your head. We just did that. So we have a double bond and we put a leaving group right next to the double bond. Okay, we can use NBS for that and then do another elimination. All right, so I'll put that over here. So we have this and we can put a bromine here because it's NBS. So to do that, we can make an alkene here and put an NBS here and put a bromine here. All right, then we do an E2 here, and you don't need a big bulky base. You can just do a sodium methoxide and you can go do this. Now this is not that hard. We've done this before. You put a bromine and eliminate. So to put the bromine, you're going to put Br2 and H nu, which is going to be quite selective, more than 90%. That's pretty much the best you can hope for most reactions. And then you don't want Kotbu, you don't want to put the double bond there, or DBU or DBN or any of those bulky guys. You want to put a nice small base, and even sodium hydroxide would be fine because again this is tertiary and you're not really going to have any SN2, so you're just going to have E2, and you can have a protic or protic, and here too you're going to have NBS H nu and let's say some solvent like this if it's still available. And here too you're going to have heat because you want elimination, and you are going to have, let's say in this case, ethanol. So that's one of the ways you can go in the reverse and try to do functional group changes. All right, so let's see what we have here. We have here a carbon, 2 carbons away from the benzene, somehow functionalized with a sulfur. Now how did that get on there? Hydrogen, is not a good leaving group. It's not a leaving group at all. So how did that sulfur get on and replace the hydrogen? obviously this hydrogen would have had to be turned into a leaving group. Leaving group, think halides, right? Or OTS. We already know how to do halogens, but the thing is we know how to do halogens here, right next to the double bond, NBS, but we never learned of doing a halogen all the way down here. So, so basically we need to have a halogen leaving group. Okay, let's draw that in. So we need to have a halogen leaving group here. Let's say I need to have a bromine here because we just found out bromines are more selective, so why not go with a bromine? Now to put a bromine there, you know, you can't really take a hydrogen that's not allylic or benzylic and functionalize it straight away. So basically we need to have a way of putting that bromine on the less substituted carbon. Ding. And that's what we found here. If you want to put it on the less substituted carbon, that's anti-Markovnikov. So you're going to have an alkene here, and you're going to put HBr peroxide and put it on the less substituted carbon. All right, so that means you're going to have this, and you're going to put HBr peroxide and do your anti-Markovnikov. All right, good. Now to make an alkene, well, we've done this before. You need a bromine and you need to eliminate. And we know we cannot put a bromine here, but why not a bromine here? And ding, you've done this before. So here's a double bond, and you can put a bromine next to a double bond, allylic bromination, and that's NBS. So we are going to put NBS and H nu, and we are going to put that bromine right next to that benzene. And well, I'm going to put that hydrogen here just because I drew it out. All you have to do is make an alkene when you have a good leaving group and a hydrogen next to it that's just itching to go with the bromine. You can put in a base. And in this case, T-butoxide is going to work because we just don't have really any other option for making alkenes except this. So we can put this. This is secondary, so this is going to reduce the chances of any SN2. So that's why we're going with a bulky base. So it'll be all E2. And then you put the bromine here on the distal end, less substituted anti-Markovnikov. Now you're just going to replace the bromine with another good nucleophile. Nucleophile in, nucleophile out. Substitution nucleophile, SN2. So you can just bring this, and this is all really set to go because it's a nice primary RX. SN2, you just bring this in as an anion. So SH minus, and obviously you need some cation to come holding hands, and then, you know, part ways when the SH then does a backside attack on the bromine, kicks it out, and then you get your SH, NABR. All right, guys, so there you go. So that's your synthesis for functionalizing a carbon that's 2 carbons away from a pi bond. All right, so just in summary, we did some reactions of radicals, mainly putting halides on them, functionalizing CH bonds that are unreactive to C halide bonds which are very reactive, using them as a launch pad to then make other SN2E2 products. And here's an alkane that's very unreactive. We functionalize that just by using light and halides. And then we are using that in a lot of applications to make different things. So I will see you next time, and we will do alcohols. See you next time. Bye.